Okay. Now, all right. So here we are. This is called chapter 15. I do actually recommend that you do a little bit of reading in this chapter. I would recommend taking a book home and say, I think I'll read, 5 pages and maybe skip a day. Then I'll read 5 pages. I'm just going to read about the things that you're teaching about because I hear you and I have my notes, but if I read it in a book, it might actually sink in a little bit better. So I do kind of recommend for some of you maybe to think about reading this chapter. All right. Do you remember the lesson we talked about what makes the, why do we even study solutions? So solutions, stoichiometry, solutions, most of chemistry is done in a solution form. God is it's pretty amazing to me to think how much water there is in this planet, how much water there is in your body, how much water there is in every form of life. Jellyfish might be 97% water, and water, we talked about this in another chapter, water has the ability to cause certain chemicals they're ionic chemicals, the ability to break those ions up, didn't they? And your brain is working because of ions. Your muscles are working because of ions. When people say, I need potassium, they don't mean that shiny metal that'll explode violently with water. No, they mean the ions of potassium. You have too much salt in your diet. Well, they're talking about sodium ions. So they have this other kind of salt, it's potassium chloride. And so you start using that salt. Still tastes salty, but you don't add a lot of sodium to your diet. When they are looking to see if you're not feeling well and they take a blood sample, they may be looking for electrolytes. Electrolytes are how you all work. They're ions. So we work on ions in water, and those are called solutions, right? So this is actually a very important chapter. If you become a biology major or a doctor, this is an important chapter. Okay, so I hope I can impress upon you that it is important. All right. Also, the word will come up all the time, concentration. What is the concentration of that solution? You get it? And here's some general words. What if I have a whole lot of solute and not much water? What would you use in general talking? Wow, that's really... What if somebody made coffee and they put a lot of coffee and not much water? Wow, that's really what? Concentrated. Or it might be strong, right? Ooh, that's really concentrated. But what if somebody makes their Kool-Aid and they reread the package wrong and you taste it, kind of tastes watery? You say, wow, it's like what? It's diluted. It's watered down, right? So we have some general words like that, and that's good. That's fine. But anyway, in chemistry, we want to be a little more exact. We want to put a number to those concentrations like that. So you understand that concentration is a ratio, yes? Okay, so if I make this right here, and if we figure out the concentration, let's say we figured out the concentration of this, all right? What if I took half of this? Let's say the concentration is, you don't know what this is. I'm going to say it's 1 molar. 1 molar, okay? What if I took half of that? What would be the concentration of half of this? 1 mole. But what about 1 drop? What about a swimming pool of this? Okay, it's 1 molar. And so the concentrations are ratios. You don't get fooled by that. Now, what are the concentration units that they've been using in chemistry over the past so many years? Well, here's one, and it says here, grams of solute per 100 grams of, what's this called? Solute's what gets dissolved, and solvent is what does the dissolving, right? So, can you imagine yourself doing an experiment like that? I go get 100 grams of water, which is 100 milliliters. I have 10 beakers. They all have 100 milliliters of water in them, okay? And then I put 5 grams in this one, and 10 grams, and 15, and 20. Am I not making a more concentrated solution? And what would the concentration units be? Grams of solute per 100 grams of water. Now, there's nothing wrong with this unit. There's nothing wrong with this unit, except it's not going to be used that often. As a matter of fact, the only time I know in chemistry that that's used is this graph. Let's go back to this graph again. All right, this is what your homework's on, is on this graph. So let's see if we can understand this graph. Look at whenever you want to understand a graph, you always look at the axes. And this says temperature in degrees Celsius. So this is freezing water, like really ice cold water. And this is boiling water. Everybody get it? Does everybody see where I'm at? Okay. And what's on this axis? Grams of what? Solute per 100 grams of water. Are you with me? Okay, so somebody did this experiment and they got these graphs. Now, what do you see here? Let's take a look. At 0 degrees, really cold water, look at this chemical here. What's this called? What's KCl3? What is that? Uh-oh. Somebody said it. Potassium chloride, isn't that right? Potassium chloride. How much can you dissolve in 100 grams of water? How many grams of this can you dissolve in 100 grams of water? 5. Is that yes? That might be one of the questions on the homework. Let's say, at 0 degrees, how many grams of potassium chlorate can be dissolved in 100 grams of water? Are you with me or not? Here's the graph for potassium chlorate. Here's 0 degrees, 5, isn't it? Now, what if we were to crank the temperature up of the water and go to 20 degrees? How many grams of potassium chlorate can you put in 20 degree water? 100 grams of that. You go up here and you say, that's 5, that's 10, that's about 8. That's about 8, isn't it? So we could actually dissolve 3 more grams in that same amount of water just by heating it up, couldn't we? What if we were to go up to, let's go to boiling. Let's have really, really hot water. And let's look up here. What number is that?
It's 55, no, 60.
Okay. Ooh, man, look at that. When it was cold water, I could only dissolve 5 grams of that in there, but when it's hot water, boiling water, 60 grams. Would you say that the solubility of potassium chlorate increases as the temperature increases? Yes. Wouldn't it? As the temperature increased, did the solubility of that increase? Meaning how many you could put in there? Yes. Okay. Let me ask this question. At 0 degrees water, what chemical on this page is the most soluble in cold water? 0 degrees. We got?
Ki, potassium.
Yes, potassium iodide, right? And this is hard to believe. You only have 100 grams of water, but how many grams of potassium iodide will dissolve in 100 grams of water, even if it's cold? How much? 130 grams. That's unbelievable, isn't it? Okay. Would you agree that some chemicals are more soluble than others?
Yes.
Okay. Now, they didn't put a lot of gases on here. In most cases, gases have less solubility when you heat them. Like if I leave a carbonated drink out and leave it in a glass and it was cold from the refrigerator and leave it outside in the room temperature, if you take a few hours later, you taste it, you said, it doesn't taste, it tastes flat, doesn't it? Because what happened is when it was cold, you could dissolve more carbon dioxide in there, and that's what gives you that little tangy taste. But when you let a lot of carbon dioxide, when it warms up, it pushes a lot of carbon dioxide out of solution. So it's not just solids dissolved in liquids. You can have gases that could be dissolved in it, couldn't you? And you guys know, I didn't know this for a long time, that I bet somewhere in biology class you learned that plants do photosynthesis, don't they? And what do they produce? Glucose, that's food. And what else do they produce? O2. Hey, that's great. And so if I have a pond and I see this little scum, pond scum, which I don't call it scum, but I know some of the names of those. Anyway, and I've studied some algae before, and so I know it's algae. But anyway, as it covers the pond, and you think, that's great, because guess what's going to happen? They're going to give off oxygen, and some of the oxygen is going to get in the water, and the fish are going to love it. Because you know the fish don't breathe water? They don't breathe water. They breathe the oxygen in the water. But guess what happens? That scum keeps going over there, and then all of a sudden, a few days later, you see fish floating to the top. They're dead. They're dead. I don't understand it. why would the green plants cause fish to die? Yes?
Blocks out sunlight so plants can't grow under the water.
Okay, now, but the plants that are growing on top, yeah, if it completely blocked off the plants underneath there, but wouldn't these algae be producing as much oxygen as some of those plants? Most of the oxygen on this planet comes from plankton in the ocean photosynthesizing. You could cut down every tree and you'd still breathe all right. Everybody thinks it's trees because in elementary school, don't they have a picture? Tree, you, or a cow. You know, cow gives off CO2, helps the plant. And you get that picture in your head and you think, wow, if they cut down all the trees, I won't be able to breathe. Yes, you will. Because in the oceans, they have all these photosynthetic plankton, all right? So anyway, where was I at? Oh, yeah. Why would you kill the fish? Okay. It is producing a lot of oxygen, but then as they keep reproducing, they run out of nutrients. Now they want to keep multiplying, but they can't. So a lot of them have to start dying. And guess what happens when any living thing dies? They have these other things called bacteria, and what do they do to the dead algae? They decompose them. And guess what they do when they decompose it? They gobble up the oxygen. So as these dead algae is being decomposed, gobble, 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 and the entire pond has almost no oxygen in it. And the fish drowned. I know you've never heard somebody tell you that. There's no oxygen for those fish. And they come up. That's called a fish kill. Well, anyway, I didn't understand that for the longest time, but can you dissolve oxygen in water? Yes. I saw another experiment where they found a way to super oxygenate water. Put 5, 6, 10 times the normal amount in there. And then you're not going to like this, but they had a little mouse and they tied a weight to his tail. And they had a great big beaker and they put the mouse in that water, the super oxygenated water, and he was just floating like this. And you say, well, he's going to drown. He didn't. Because every time he let that water come in his lungs, it was full of what? Oxygen. Now, for me, that would freak me out. It would freak me out to let water come into my lungs. But I wonder, will that ever happen? Will we ever get to the point where we could teach ourselves to, if we had a super oxygenated water or something like that? Anyway, I'm getting off the subject a little bit here. Let's go back to our chart here. Let's go to, let's start using some fancy words here, okay? Let's say that let's do the same one. Let's do potassium chlorate again. At 0 degrees Celsius, if you put 5 grams in 100 grams of water, then you are what they call saturated. You've made a saturated solution. It means you try to put more than 5 in there. What if you try to put 6 grams in there? A gram of it's going to fall to the bottom, and I don't care how much you stir it, it won't go into solution. You get that? 5 is the max. So if you have 5 in there in 100 grams of water, then it's called a saturated solution. What if you only put 3? Saturated means completely full. What if you only put 3 in there? Is it saturated? No, you could have put more, couldn't you? So what's a great word that means not full? What if you only put 3 grams in there instead of 5? What word would you use? Unsaturated. Ooh, I like that. Okay. Now, let's go here. Let's heat this up. At how many grams of potassium chlorate would you need to make a saturated solution at 100-degree water? 100-degree water, you go up here till you hit the graph. You read across there, 60. What does that mean? You had to put how many? 60. If you put 60 grams of potassium chlorate in 100 grams of water, then it's saturated. What if you only put 30? Unsaturated. How about 29? How about 2? There's a whole bunch of unsaturated. There's a whole bunch of ways to make it unsaturated, isn't it? Only one way to make a saturated solution. I'm looking at your faces. When you do the homework tonight, those are the words going to come up. Now, I'm going to show you a video here in just a minute under very special conditions. Here's what you could do. What if I were to put 60 grams in this really hot water? And let's say the beaker is very clean, it's kind of, not a lot of scratches and that kind of thing. And then I simply take that beaker and set it and leave it alone. Leave it alone. What's going to happen to the beaker? What's going to happen to the temperature?
It's gonna get colder.
That's all right. And guess what? As the temperature of water gets cooler, you're not supposed to be able to hold 60. So let's say it goes down, it cools down to, let's just make up a number. Let's say we cool it down to 45 degrees Celsius. You're only supposed to be able to hold 20, but you still have 60 in you. What normally would happen is 40 grams would fall to the bottom and only 20 grams would still be in solution. But under special situations, if you have a nice clean beaker and nobody jiggles it and jars it and that kind of thing, some chemicals, when you cool it down, they will not come out of solution. So at 45 degrees, you're only supposed to put 20 and you put 60 in there, and I don't see any of it coming out. Then what special name would you give to a solution that has way more than they are supposed to be able to hold?
Oversaturated.
Yeah, but they use another one. I even like it better than oversaturated. Super saturated. Now, if you do have a supersaturated solution, it's very unusual. It shouldn't happen. And I can tell you what's going to happen. That's what you're going to see on the video here. If I take one crystal of that chemical, and I simply throw it in the beaker, that's all it was waiting for. It was waiting for something that's called a nucleation center. I'm not going to get fancy on that. But it needs some place to start forming the crystals that come out. And so if you throw one little crystal in there, go, and all that 40 that's supposed to come out will start growing on that one crystal. Now, sometimes in elementary and middle school, they do this on purpose. They make a supersaturated solution, and then they let it cool down, but then they ask you to put a pencil across the top and a thread and maybe a paper clip or something like that. Have you ever done any of this in any of your classes? Middle school? Elementary? And then what happens if you're patient, you just wait a few days, what happens when you pull the string out? Lots of crystals in there, see? And you can and any of you who want to, do it in the next 2 weeks, because it does take a while to make crystals, but if you can document yourself making crystals at home, you can go to the grocery store, the pharmacy has a lot of different chemicals that you don't think about. Epsom salt. You can make crystals out of Epsom salt, okay? And it's called magnesium sulfate. You can make it out of regular table salt. You can make it out of sugar, okay? When you go to the fair and they have rock candy, that's what they did. They made a super saturated solution. They put these sticks in there, and the sticks are kind of coated with a little bit of sugar on them anyway. They put a lot of food coloring in there, and then they put it in there and they pull them out, and then you can make your crystals grow on the sticks like that. In the pharmacy, they also have things called alum, A-L-U-M. A lot of people use that for cooking, like making pickles and stuff like that, alum. What's another thing you can get in the grocery store? I already said sugar. Anyway, and if you're really, really if you get good at making crystals, say, I'd like to make something else. I'll even give you some of this stuff here. If you'd like to have some copper sulfate. If you look back there on that poster, way back there on the top, the black poster, that's a student who made crystals one year. Yes, it takes a while. They're not instantaneous, but it takes a little while. The one you're going to see on the video today is going to be instantaneous. They're going to put a seed crystal in there, and I'll show you at least 2 videos of it. I think you'll like this. It's pretty neat. Remember, supersaturation is kind of unusual. Unless I tell you, unless you know that it's supersaturated, that you can't just assume it is. Is everybody okay on this graph? You think you know how to understand that graph?
Yeah.
Let me pop this up here. Boing. Which one? This one? Yeah.
So one little crystal.
Zoom in, Rena. I don't know how. Go closer. Hold on.
Just start.
You can't even see it. Okay, go.
Hardly see.
Okay,
Right
but
now.
The reason he has a watch glass over there, he doesn't want dust. If dust gets in there, it might crystallize.
Ready?
Oh.
So realize this has been sitting there all year long like this. Okay?
What is it?
I'm
What
gonna
is it?
change it.
That's a brand new beaker too.
Well, it's water that has a huge amount of these crystals dissolved in it.
Oh.
It has so much of it that is called supersaturated. It actually is holding more salt than water actually can.
Just waiting for a pattern.
Because I boiled it.
You dropped it in there?
Oh,
What?
Oh snap!
oh my gosh, that's so cool!
It looks
like a
it looks like a
Sodium
football.
acetate happens to be the ones that chemistry teachers like to use because you can do it instantaneously.
So cool.
What happened to the bug?
What happens if it's still over there? Ow!
That was just one.
You understand it's growing. The crystals are supposed to fall to the bottom. They're simply attach themselves to a pattern, and the crystals are growing.
Yeah, I get them first.
Watch it.
I want to see my nail. I want my nail to be in the picture.
Oh my gosh, like this is giving me goosebumps.
It does look kind of weird.
This is so cool. Is this real? They look like feathers.
Can we touch it? Are we gonna hold it?
Wait till it's all crystallized.
You would touch it either way because
I
I
would.
touch radioactive things. Oh my gosh, poor Austin.
You can't see like that. Rita, stop.
He's having more fun.
By the way, when a thing crystallizes, it also gives off heat. And there's a company who you can, if you're a hunter, they can buy these little packets and you put them in the microwave to make sure it's all dissolved. You take them, put them in your socks, your pockets, and you push a little button. And the button, a little seed crystal comes out there, and it makes the bag, supersaturated bag, crystallize, and it gives off heat for about 2 hours. Has anybody ever done that? Gone to a ball game or somebody gave you pocket warmers or something like that? Most of them are based on a supersaturated solution like that.
Are you sure?
Let me stop this one and maybe show you another one.
Why are you pushing me? I want to touch.
Okay, so let me get to another one. I don't know if this is it. Whoops. Which one did I want to show you?
At Harvard Business School, we have a unique approach to online learning.
Again, the reason this is used in a lot of chemistry because it can make crystals very quickly right in front of you. Copper sulfate, you'd have to wait days to be able to do that.
We've been talking about supersaturated solutions, and we discussed rock candy and how you can make a supersaturated solution of sugar, but over time, that extra dissolved sugar will slowly crystallize out and form that candy. However, it takes quite a while. Even when I do my special method with the sugar, and I put some sugar crystals on the string in the rock candy, it still takes a matter of hours for it to happen. The absolute best supersaturated solution you can get is sodium acetate. Sodium acetate dissolves in water to the tune of about 90 grams of sodium acetate to every 10 grams of water. So it's extremely soluble in hot water. So you heat the water up to maybe 80 degrees Celsius, you can dissolve a lot of sodium acetate. When the solution cools back to room temperature, all that extra solid should crystallize out, but it doesn't. These are solutions of sodium acetate, all supersaturated solutions. They are very stable, unlike sugar, which after a week or two will begin to crystallize no matter what you do. Sodium acetate, as far as I can tell, is permanently stable. I last used these test tubes back in May. It's now the end of October, it's almost November, and these have been sitting in my cupboard since then, and they will probably continue to sit there for as long as I want. So let's take a look at what happens if we add a crystal of sodium acetate to one of these test tubes. I'm going to take one little crystal here on my finger, and let's drop it in that liquid. The instant we do that, the sodium acetate begins to solidify. It is crystallizing so quickly, the liquid can't even run out of the tube. Sometimes if you get a little air bubble to go up there, it'll start crystallizing from the top. But eventually, that entire tube is going to solidify. Now, based on the things we've been talking about in chapter 15, What's the one word we would use to describe this process? Answer, of course, should be spontaneous. This process occurred spontaneously.
Okay. Let's see. I think I'll make sure one more, or that may be it.
It's very.
Can I have
Eliza! It's like. I want to see. Episode 30. Miss S, come look at this. You just saw it.
My job is to make college easier because students have a lot on their minds.
Have you seen crystals of salts? Crystals are made through a process of
Well, go through this a
crystallization.
little bit.
Let us try to make
But he's
salt
gonna
crystals
use
from a
copper
solution of-
sulfate,
a
okay?
saturated solution of copper sulfate and copper sulfate. First, we will make a supersaturated solution of copper sulfate. Light the spirit lamp. Place the copper sulfate solution on the burner. Heat the mixture. Now keep on adding copper sulfate till no more salt is dissolved. Fasten a thread on a support and suspend it in an empty glass.
By the way, if you
This
want to grow
thread will
crystals,
act as
there's a
diffusion
100
sensor
recipes
to the
online.
container.
You can just,
Now remove
you know,
the
some of them
solution
are
from the
better than
burner.
others.
Pour the solution in the glass.
I've seen it where you actually put some crystals and tie one on to the string, but the string is rough enough to have crystals form on it.
Leave the glass aside for a few days.
So it's hot right now, and as it cools down, shouldn't be able to hold it, so they have to come out somewhere. You just have to
We
give
see
it
salt
someplace.
crystals formed on the string.
This is several days. But they're beautiful, aren't they?
This happens because the solubility of salt in water
Okay.
increases.
Anyway, that's what I want to show you. What do you think? Do you understand this? Okay. So what we'll do is, let's see, this class is over at 10:50. Okay, so I got to make sure I wrap it up here. So the homework you're going to have has to do with this chart, and I'm going to ask you if you have any questions on that. So let me, yes.
Oh, I don't have a question on the homework. I just had a question. Can you eat these crystals?
Okay, now, if you make them out of sugar, then the answer is yes. Now, I wouldn't eat the ones made out of salt. They're kind of, but you could. But sugar, you could actually do sugar. Maybe you could try different kinds of sugar. What if brown sugar acts the same way as white sugar? I don't know. I've never had anybody do that. Anyway, you could do any of these chemicals. I saw one video, they used potassium nitrate, and the only problem with that is you use a ton of potassium nitrate just to make crystals, so I didn't want to waste all the chemicals there. All right, you okay on this? You think so? All right, so I'm gonna do a couple more things, and then I'll end your homework assignment to you. And let's go down here, and what you'll see is the next thing you might, next kind of a concentration unit you might have is, and this doesn't even have a special name to it, the one we just talked about, grams of solute per 100 grams of solvent. The only place I've ever seen it is the solubility curve. That's the only place I've even seen it used. This one was used all over the place. It's still being used today, but not by chemists. All your biologists tend to make their solutions like this. It's grams of solute per 100 grams of solution. Now this is where we're going to get tricked a little bit, okay? One of the questions on the test, you don't have the test for a while. I mean, it'll be a little while for a test. What if I had 3 grams of salt and what if I had 6 grams of water? Then what is the percent? This is called percent composition solutions. What is the percent of salt? What would you call the solution? And what you have to remember is it's grams of solute. So you got 3 grams over grams of, what's it say? Solution. Well, how many grams are in the solution? Don't you have to add these up? Aren't there 6 grams of water and 3 grams of that? So what's that give you? 9 grams of solution, right? So what is the percent composition for this thing? What is this in a calculator or in your head? It's 0.333, also known as what? 33.3%. So what did we make? We made a 33% salt solution. Now, The reason that people still use it today is so simple. I take the grams of the solute, I divide by the grams of everything put together, and there it is. All I need, you know what I need? I need a balance. I need a balance. That's the only equipment I need to make this, and some kind of beaker or bowl or whatever. And so these are so easy to make. And you say, why didn't the rest of the world just stay right there? Just say, that's plenty. This is plenty. Well, you know what happened. Can you tell me what happened? Why did chemists say that's not going to work for us? As a matter of fact, this is called percent. You know percent means per hundred?
Yes.
Well, guess what? You could have parts per hundred, called percent. You could also have parts per what? You could have parts per thousand. You could have parts per million, parts per billion, parts per trillion. Those are all the same idea. It's the same idea. Parts per hundred is percent. Get it? Anyway, so all of these have to do with the same idea. And people still use them today. They do. But the chemists, in chemistry book, you won't see them making solutions in percent. Yes?
Why is there 100 like under by the solution? It's like 100 grams of solution.
Which one? This one?
Yeah.
Okay. Actually, it doesn't have to be 100. That's a good, excellent question. Excellent question. You're right. The only reason they said 100 is because they want to be parts per 100. But if you just do what we did, that is parts per 100, because percent is the same. Excellent. That's an excellent insight you had there. They could have simply said grams over grams, and it would have automatically been percent. But by putting 100, I guess that's what they did. You're right. They didn't really have to do that, did they? I like that. That's really good thinking. All right. Well, anyway, all of these have to do with that. And there are people who still make solutions that way, but not the chemist. The chemist, this is the one you're going to talk about from now on. From now until the end of this chapter, the one we're going to spend all of our time on is that guy right there called molarity. Now, what's the definition of molarity? It's not grams, but what? And you know what's going to happen. You know what they wanted. You know why these didn't work? It didn't work for chemistry because how quickly can you... What if I said, hey, it's a 40% salt solution. Yeah, but how many moles of salt are in there? Well, I don't know. See? It's very difficult to get in the mole world. And remember that word called stoichiometry? The key to stoichiometry is how fast you get in the mole world. The faster you get in the mole world, see that? You can go anywhere. And so this wasn't going to do it for them. So here's what they did. That sounds weird. Hello out there, chemistry land. You know these things have been using for concentration? No. We're going to make a new word. A new word. One you haven't ever used before. Yeah, what is it? Molarity. What's molarity? It's moles of solute per what? Liter of solution. Why would you do that? Why would you do that? Why would you make a new one? And I'll show you right here. That's right here. Ready? What is moles per liter? That's molarity. Times volume in liters. What's moles per liter times liters? If I make a solution and I know the molarity and I only use a little bit of that and I know the volume, what is molarity times volume? Help me out here, okay? What's moles per liter times liters? Cancel.
Moles.
Yes. I'm in the mole world just like that.
Yes.
And that's why they did it. And you know what they didn't like? Oh, by the way, everybody's got to have a brand new kind of a glassware that no one's ever made before. And by the way, it's going to be expensive because these are a little hard to make. And you got to make sure that line's exactly in the right place. These are called volumetric flask. And they're used to making solutions in chemistry. And if I have a bigger one back there, made a liter, I could put so many moles of something in there and fill it up to the top with water, not the top, to the line, and that would be a, quote, 2 molar solution. I don't even know how much water I put in there. I don't even measure the water. I just make sure the water goes up to that line so that the solution is 1 liter. And so everybody had to have a new piece of glassware. Matter of fact, this one's only 100 milliliter, and I have 1,000, 500, 200. You can buy lots of different kinds of volumetric flasks. But if you stay in chemistry and you make solutions, you'll use the volumetric flask. Why? Because they came up with a new definition for concentration. Molarity is a concentration unit, okay? Big M is not moles. What's big M stand for?
Molarity,
And what's molarity stand for?
concentration.
Moles per what? Moles of solute per what? Okay. All right, let me give you your homework. Now, even though the homework is not that hard, please make sure you do it on your own. And if you have trouble, see me in the morning. But here's the questions you have to answer, and here's the graph. Now, I could have printed on 2 different papers, but isn't this the same graph I gave you anyway?
Yes.
So if you don't like doing this, why don't you just lay it right next to the side of your graph in your packet? How about that? All right, what you do tomorrow, and if you have some trouble, before you turn it in, I'll let you ask me some questions. There you go. And take one of those. But it's very important that you do these on your own, and if you have trouble, then you'll know what kind of question to ask me tomorrow, and then you'll be in good shape. All right, we have a couple more minutes. If you want to start it, if you want to start the homework, we still have about 3 or 4 minutes. So if you want to start it, do like the first couple of questions. Yes.
Sir, what does that equation say?
Oh,
Kind of light, I can't.
and I'll actually show this to you tomorrow, but it says molarity times volume equals moles of solute. And David, that's a great question. So I'm going to go to the front of your packet, David. And here we have percent by mass. That's the one we just talked about. And then we're going to do some more about this tomorrow. Molarity. I'm going to spend a lot of time with molarity tomorrow, okay? And then, let's see how tricky you are. You guys know about math?
Yes.
Do you know if I take that equation and multiply both sides times liters? There it is. This is the same. Don't tell anybody. These are the same equation, just rearranged. What's molarity times volume in liters? Moles of solute. So we'll do a lot of this tomorrow. Tomorrow we'll do a lot of mathematics with solutions, and you'll turn in your graph. And then, anyway. Okay. Once you, again, if you have time, maybe look at the first couple of them and say, hey, I think I can do this. And if you, like I said, instead of flipping it back over, the packet that I gave you has that same graph on it. So if you just lay them side by side, you don't have to keep flipping them back and forth like that. Also, I want you to be as careful as you can. If you said, you can't say, oh, I think it's about 80. If it's 82, put 82. Don't put 80. If it's 82, put 82. All right, there we go.